In February 1943, at the edge of Boscombe Down airfield in Wiltshire, a group of technicians gathered around an unfamiliar aircraft. It was a supermarine Spitfire Mk XVIII, but its slender wings had been replaced by new, reinforced panels carrying two long-barreled Vickers S 40mm cannons. The barrels extended beyond the propeller's disc, their muzzles capped with canvas covers to keep dust out of the bores. Under the winter light, the gunmetal caught a dull reflection, heavy and industrial against the Spitfire's narrow frame. A ground crew chief noted the added weight in his maintenance log: total armament load, 370 pounds per wing, balance adjustment required on elevator trim. The Vickers S, originally designed for use on the Bristol Beaufighter and the Hurricane IID, fired high-velocity 40mm shells at 600 meters per second. Its single-shot recoil measured over 1 ton of backward force. No Spitfire before had carried such a weapon. At 9:40 hours, test pilot squadron leader James McKenna strapped in. The propeller of the Merlin 45 coughed, then steadied into a smooth rhythm. Observers from the Air Fighting Development Unit took positions along the grass perimeter with notebooks and cameras. As the aircraft taxied, the cannon barrels vibrated slightly, causing the nose to dip. McKenna eased the throttle forward. The modified Spitfire lifted off at 125 miles per hour, wheels tucking in slowly under the strain. From the control van, Flight Lieutenant Parr recorded airspeed and climb rate. The extra mass reduced the initial climb to 1,700 feet per minute, 1/3 lower than standard, but the airframe remained stable. McKenna leveled at 6,000 feet and began a shallow dive toward the Salisbury Plain gunnery range. The test protocol called for 2 firing passes on obsolete Churchill tank hulks positioned at 30-degree angles to simulate side armor shots. At 2,000 yards, McKenna armed the cannons. The first round struck short, kicking dust before the target. The second hit squarely through the turret roof. Observers saw a flash and a plume of grey smoke rise from the wreck. Each gun's recoil jolted the aircraft several feet upward, but McKenna kept control. The vibration loosened several rivets along the wing root, later marked with red chalk during post-flight inspection. When he landed, the chief armor examined the spent shell casings lying near the wing fairings. Each measured 40 by 158 mm, solid brass, marked Vickers S Lot 14 1943. Engineers found no distortion to the mountings, though the recoil absorbers showed early signs of fatigue. In his report, McKenna wrote, "Handling degraded but acceptable. Accuracy at 800 yards satisfactory. Recoil manageable. Visibility on dive approach limited." The Air Ministry Observer summarized the morning trial: weapon viable for low-altitude attack if structural reinforcement maintained. Further assessment required for ammunition feed reliability. Behind the observation tent, an unmarked crate bore the initials HP, Vickers design section. Inside lay a revised breech assembly meant to reduce weight by 7 pounds. The lead engineer, Harold Percival, had designed it 2 years earlier for a project that had been quietly cancelled. The Army had judged the 40mm too heavy for aircraft use. Now, under renewed interest in anti-armor air power following the North African campaign, his rejected cannon was being reconsidered. As the team packed the equipment, the afternoon light fell over the runway, outlining the Spitfire's long shadows across the grass. The day's data, coded as Trial Report AFDU Spitfire 5S-12, would be forwarded to Farnborough for ballistic review. No commentary, no prediction, only figures: muzzle velocity, dispersion pattern, structural strain. But in those numbers lay the quiet beginning of a transformation that would turn a pure interceptor into a precision tank destroyer. By late March 1943, the modified Spitfire arrived at the Royal Aircraft Establishment, Farnborough. It was designated Spitfire Mk XVIII, Special, 40mm S installation. The hangar floor bore fresh chalk lines for structural calibration. Technicians from Vickers Armstrong and the RAE Engineering Division began measurements under the supervision of Air Commodore Anderson. Every component was logged by serial number, gun mounts, feed trays, electrical firing circuits, and recoil dampers. The Vickers S cannon itself measured 7 feet, 3 inches in length. Its breech block, a forged steel cylinder machined to within 0.02 of an inch, was mounted directly beneath the wing spar. Percival's revised design incorporated a shorter hydraulic buffer and an angled cradle that distributed recoil along 2 longitudinal beams. The modification was simple but effective. When fired, the entire impulse was absorbed by reinforced wing ribs rather than the fuselage. Tests began at 9:15 on April 3. The aircraft was secured in a ground-firing rig made of timber blocks and steel restraints. Technicians placed dummy shells, marked inert, ballistic test, into the magazine chutes. Each firing sequence was triggered remotely from a control booth 30 yards away. A microphone registered the pressure wave. Accelerometers along the wing route captured deflection data at 1/1000 second intervals. On the first discharge, a visible shock pulse rippled across the wing skin. Instruments recorded a 0.43-inch flex at the cannon's midpoint, within safe tolerance. The reinforced spar, fabricated from duralumin alloy L.157, absorbed the stress without cracking. By the 5th shot, oil seals on the left buffer began leaking, a recurring issue noted in previous Beaufighter tests. Engineers replaced the seals with a heavier rubber compound. After the 12th firing, observers from the Air Armament Experimental Establishment entered the hangar to inspect the gun mounts. The barrels showed faint heat distortion, rifling remained sharp. The cannon's automatic feed, driven by compressed air, cycled at 90 rounds per minute but was limited to single-fire operation for accuracy. McKenna, the test pilot, examined the ammunition belt, each shell fitted with a 2.9-pound high-explosive projectile. "It feels like firing 2 shotguns at once," he noted in his log. Outside, 2 damaged Panzer III turrets retrieved from North Africa were positioned in the range field beyond the hangars. At 400 yards, the Spitfire fired single rounds under controlled conditions. Each impact left a clean puncture through 50 mm of armor plate. The projectile fragments created secondary spall, scattering metal shards inside the turret interior. Observers measured the penetration angle and entry diameter precisely, 38 mm across, with a slight lip of deformed steel. Farnborough engineers compared the results against the standard Hispano Mk II 20 mm cannon. At equivalent range, the Hispano shell embedded without penetration. The difference was decisive. In the Ray's Memorandum AF Giengit 5443, the conclusion read, 40 mm Vickers S offers 2.3 times armor penetration capability of Hispano round, though at reduced firing rate. Tactical deployment to be limited to trained pilots for ground attack application. Percival watched the test silently from the observation balcony. His earlier proposal for the same gun had been dismissed in 1941, deemed unsuitable for fighter carriage. Now, the very weapon once labeled impractical was being studied for operational issue. Within days, the Air Ministry approved conversion of 6 Spitfire Mk V airframes to Type T standard, the T for tank buster. At dusk, mechanics rolled the prototype back into Hangar 4. The smell of cordite still lingered from the range. Under the overhead lamps, the cannon muzzles glowed faintly from residual heat. Every mark, every note, every trace of powder was recorded into the RAE trial book. No speculation, no forecast, only observation. The Spitfire, a symbol of aerial agility, was being methodically reshaped into a weapon of precision and brute efficiency. By July 1943, the first operational evaluation of the 40 mm armed Spitfire began at RAF Henlow. The aircraft, still marked as experimental, carried desert camouflage and an enlarged radiator beneath the left wing. Each was fitted with 2 Vickers S cannons, one Hispano 20mm for sighting, and a strengthened undercarriage to manage the recoil loads on takeoff and landing. Flight records show the center of gravity moved nearly 4 inches forward. Pilots were briefed to keep nose-heavy trim until the gear retracted. At 6:20 hours on the 14th of July, Flight Lieutenant John H. Gibbs took off for the first live-fire trial beyond the British coast. His orders were to engage derelict tanks positioned along the chalk cliffs near Lulworth Cove, simulating field conditions. The temperature was mild, wind at 6 knots from the southwest. At 5,000 feet he rolled into a shallow dive, airspeed increasing to 280 miles per hour. The first 40mm round hit short, the second penetrated the target's turret at a 35-degree angle. The flash was visible even from the observer's post 2 miles away. Gibbs reported minimal control loss, though the recoil raised the nose nearly 5 degrees. From the ground, engineers marked each impact and collected fragments for metallurgical analysis. The post-test memorandum recorded penetration through 50mm of face-hardened armor, a result equivalent to that of a 6-pounder anti-tank gun. The same report estimated the effective firing envelope at between 400 and 800 yards. At greater ranges, the projectile's drop became too steep for accurate sighting. The guns were rebore-sighted with a downward convergence of 2.5 degrees to compensate for dive attacks. By late August, 2 prototypes were shipped to the Middle East for operational evaluation under No. 103 Maintenance Unit in Egypt. There they joined mixed formations of Hurricanes and Kittyhawks engaged in convoy interdiction. Official dispatches mention the Spitfire T only in technical addenda, but pilot diaries preserved at the Imperial War Museum provide clear details. One entry, dated the 21st of September, 1943, reads, "First sortie with 40mm guns today. Heavy, slow on climb, but hits with the strength of a cannon from a ship." The most revealing data came from the armorers. Each aircraft carried only 15 rounds per gun, limiting firing time to a few seconds. Yet the destructive power was exceptional. In a single pass against a derelict Panzer IV, one Spitfire destroyed the turret ring and cracked the hull plate. Gun camera film, later analyzed by the Directorate of Armament Development, showed projectile velocity consistent with ground-fired tests, approximately 600 meters per second. Recoil deformation along the wing route was measured at 0.4 inches, identical to Farnborough figures. Operational observers noted, however, that the added weight degraded maneuverability and climb performance to a degree unacceptable for frontline fighter duties. The Merlin 45 engine strained at high temperature, and prolonged dive recoveries risked overstress on the lower wing spars. Even so, the combination of accuracy, recoil management, and structural endurance impressed commanders enough to request 6 more conversions for continued field testing. According to the official RAE report issued in October 1943, the cannon's penetration data matched that of ground artillery within close range. At 800 yards, 40mm rounds could pierce the side armor of a Panzer III. At 600 yards, they could breach a Tiger's track assembly. The report stated, without embellishment, that a Spitfire equipped thus could disable enemy armor with single-shot accuracy when employed in dive or oblique attack. That realization changed the perception of air-to-ground warfare within the RAF. For the first time, an interceptor born for air superiority had demonstrated the ability to deliver concentrated anti-armor fire. No longer a graceful dogfighter, the Spitfire T had become a precision strike platform. The numbers, photographs, and shell fragments proved it. The last test flight of the summer ended at dusk, the aircraft taxiing across the dusty airstrip with both cannons empty and the smell of burnt powder lingering in the slipstream. Mechanics lifted the engine cowlings to check for cracks, none were found. The day's figures were entered into the flight log and forwarded to the Air Ministry under the notation operational potential, limited by range, not by firepower. What began as an abandoned design on a factory shelf was now altering the definition of what a fighter could do. The 40mm Spitfire was heavy, temperamental, and inefficient as a pure interceptor, but in the language of engineers and ordnance specialists, it had achieved proof. By the winter of 1944, the 40mm Spitfire program had reached its conclusion without fanfare. Official correspondence from the Air Ministry, dated the 12th of January, recorded the decision in 10 plain lines: further development of the Vickers S installation in Spitfire airframes is to be discontinued. Resources to be redirected to Typhoon and Mosquito strike units. The note carried no criticism, only the logic of wartime efficiency. Production space at Vickers Crayford plant was already at capacity. The Spitfire T's armament could not be standardized across squadrons. At Boscombe Down, 2 surviving prototypes sat in Hangar 3 under canvas. Their once glossy desert paint had dulled to chalk. The test markings, white circles denoting rivet strain points, were still visible along the wings. One engineer, Sergeant M. Lee, photographed the airframes before disassembly. His negatives, preserved in the Imperial War Museum, remain the only visual record of the type. In his logbook he wrote a single line: all data transferred to Typhoon installation study. That transfer proved decisive. The recoil distribution system Harold Percival had designed for the Spitfire's narrow wing was adapted directly into the Hawker Typhoon's 40mm mounting tests later that year. The angled hydraulic buffer and reinforced spar beam became standard features in the Typhoon's anti-armor configuration, improving survivability during repeated firing passes. What had begun as a cancelled prototype quietly informed the design of one of the RAF's most effective ground attack aircraft. In operational reports from the 2nd Tactical Air Force, engineers credited previous trials of Vickers S on Spitfire for the improved recoil dampers used in field conversions. No press statement was issued, and the Spitfire T designation never appeared in combat statistics. Yet in practice, its influence extended through the lineage of British strike aviation, from the Typhoon to the Mosquito FB Mk XVIII, which carried the same cannon in its TDC anti-submarine variant. Post-war assessments revisited the experiment with quiet respect. A 1946 RAE memorandum titled Aircraft Armament, Lessons of 1943–45 cited the Spitfire T as the first British single-seat aircraft to achieve consistent penetration of armoured targets. The report concluded, though unsuited to sustained field operation, the installation validated heavy-caliber precision attack from a fighter platform. Subsequent designs owe to its empirical findings. In interviews recorded at Farnborough in 1948, Percival spoke briefly of the project. His tone, captured on reel-to-reel tape, was detached but firm. The gun worked. The airframe worked harder. We learned what the limits were. There was no bitterness, only the measured certainty of an engineer who had seen his concept survive long enough to teach others. On a clear day that same year, one of the original 40mm barrels was placed in the RAE Museum collection. The tag attached to its breech reads, Vickers S, Spitfire Installation, Boscombe Down 1943. Nearby, the display note summarizes its legacy in 14 unemotional words: prototype system demonstrating feasibility of high-caliber aircraft armament for precision strike. Viewed in isolation, the weapon seemed excessive for the elegant lines of the Spitfire. Yet its existence marked a shift in thought, from aerial dueling to tactical destruction, from pursuit to precision. The transformation was not declared in speeches or communiques but written in test sheets, recoil graphs, and fragments of pierced armor stored in wooden crates. In the long record of wartime aviation, the Spitfire T remained a footnote, one that quietly connected the world's most famous fighter to the industrial, ground-focused warfare of the late 20th century. Its cannons never entered mass service, but their data shaped every British aircraft that followed. When the final airframe was scrapped in 1946, only the engineers noted its passing. The records closed with a single line typed in black ink, "Program concluded, knowledge retained." And in that phrase, the legacy of the rejected cannon endured, proof that even abandoned experiments could redirect the course of modern air warfare. By 1945, traces of the 40mm Spitfire lingered only in archives and prototype fragments. Yet within the technical branches of the RAF, its lessons had already been absorbed into new doctrines. The Fighter Command reports of March that year referred to precision low-angle engagement procedures, a phrase derived directly from the Boscombe Down gunnery trials. In effect, the Spitfire T had proven that a single-seat fighter could deliver anti-armor fire with accuracy approaching that of a field gun, if the pilot could survive the dive. At Farnborough, engineering staff compiled a synthesis of all flight and ballistic data. Each figure was plotted on linen graphs: muzzle velocity, dispersion angle, structural stress, dive trajectory. The average impact deviation at 600 yards measured just 0.8 meters. The cannon's recoil impulse had reached 11,400 pounds, absorbed across 43 rivet points per wing. Those values became reference standards for every subsequent heavy armament installation studied during the last months of the war. In the same period, British observers attached to the U.S. 9th Air Force compared their Typhoon and PF-47 results with the Spitfire trials. They noted that while the American Thunderbolt could carry larger bomb loads, its ballistic accuracy against moving targets was inferior. The Spitfire's compact form and high-speed dive gave a brief but valuable window for attack. The post-mission summary read, "Effectiveness of cannon strike proportional not to rate of fire but to precision of delivery." The principle, born in an abandoned test hangar, shaped post-war discussions of close air support tactics. When the Air Fighting Development Unit drafted its final wartime evaluation in September 1945, the Spitfire T received only a paragraph. It acknowledged that the weapon's accuracy, not its power, had redefined expectations for single-engine aircraft. The 40mm installation, it stated, demonstrated the practicality of deliberate, single-shot gunnery as opposed to rapid-fire saturation. The language was reserved, but the meaning was clear: technology had met control. Across the Channel, captured German technical officers studied the same data. Interrogation transcripts preserved at the Imperial War Museum show that engineers from the Luftwaffe's armament department requested copies of British recoil distribution diagrams. They recognized the similarity between Percival's system and their own projected Mk 3.7 installations for Ju-87G dive bombers. In a quiet reversal, each side had pursued the same problem: how to make a lightweight airframe fire a weapon built for a tank. Percival himself returned to Vickers in late 1945, where he was assigned to jet-age ordnance development. His design notebooks from the Spitfire project remained on his desk for the rest of his career. One page, dated 1943, contains a penciled note in the margin, "Every recoil teaches." It summed up an engineer's view of progress: incremental, often unseen, measured in failure survived. By the end of the decade, the influence of his rejected cannon could be traced in the first generation of jet fighter bombers. The Gloucester Meteor F.8 trials used recoil-mounted instrumentation nearly identical to that tested on the Spitfire T. The Hawker Sea Fury strengthened wing box, rated for 20mm and 30mm guns, borrowed its geometry from the same drawings. Even in early Cold War manuals, references to Spitfire-type damping brackets persisted as shorthand for reliable heavy gun mountings. No monument marked the experiment, but its effects spread through procedure, not propaganda. Pilots trained after 1945 learned control dive profiles derived from the Lulworth Cove data sheets. Armament officers calculated recoil ratios using Percival's tables. Historians would later describe the shift as the moment British air power crossed from improvisation to applied engineering. In the silence of the RAE storage vaults, one of the original barrels still bears the faint chalk number S12. The bore is pitted, the steel dark with age. Nearby lies a small envelope of film negatives showing the Spitfire firing at a rusted tank in 1943. The image is grainy, the aircraft barely discernible against the dust. Yet in that frame exists the bridge between two eras, the instinctive ingenuity of wartime necessity and the measured precision of the technological age that followed. From that experiment came no victories, no squadron citations, and no medals. But in the language of design, it left a mark that endures, data instead of glory, proof instead of praise. And for those who read the reports years later, the message was unmistakable. Even a weapon once dismissed as impossible could, through persistence and measurement, change the logic of air warfare. By the early 1950s, the Spitfire T existed only in a handful of photographs and line drawings, but its engineering echoes were everywhere. In the classrooms of the Royal Air Force Technical College at Henlow, instructors still used Farnborough's recoil distribution diagrams as examples of applied load transfer in stressed skin wings. The 40mm experiment had quietly become a teaching tool. Every post-war armament engineer learned the same lesson: control recoil, and any gun could fly. At the aeroplane and armament experimental establishment, the arrival of jet propulsion shifted attention toward new calibers and higher speeds. Yet the same hydraulic principles from Percival's 1943 buffer system appeared again in the armament design notes of the Hawker Hunter and the de Havilland Venom. The evolution was subtle but traceable, each aircraft capable of firing heavier rounds without compromising stability. The Air Ministry's 1951 report on heavy cannon integration in jet aircraft opened with an acknowledgement that previous empirical data from piston-engine aircraft remain valid. Those data were the Spitfire Ts. In an interview recorded 2 decades later, Squadron Leader McKenna, the pilot who first fired the prototype at Boscombe Down, described the experience with characteristic understatement. "It kicked," he said. "But it told us what a fighter could take." His words reflected the sentiment shared by the generation of test pilots who bridged 2 ages of flight, from propeller to jet, from instinct to instrument. At Vickers Archive in Weybridge, the surviving engineering drawings reveal how narrow the line between rejection and innovation had been. The original 1941 proposal bears a red stamp, "Project Shelved." 2 years later, the same drawing, annotated with Percival's notes, was stamped again, "Approved for trial." Between those marks lay the story of British wartime engineering, skepticism, necessity, and eventual validation through evidence. By the time the RAF introduced the Hunter F.4 in 1955, every principle proven by the 40mm Spitfire had been standardized: reinforced wing spars, recoil buffers, and staggered fire control to prevent asymmetric loads. Even the cockpit gunsight trace, calibrated for steep, short bursts, was modeled on the dive profiles perfected over Lulworth Cove. The Spitfire's tank-busting variant had vanished, yet its fingerprints shaped the DNA of modern ground attack tactics. In post-war doctrine papers, British strategists began to speak of precision intervention rather than mass strike. This language, subtle but deliberate, reflected the transition from wartime improvisation to scientific warfare. The Spitfire T's data sheets had proven that precision could be engineered, that accuracy was a measurable product, not a matter of luck or pilot instinct. Percival never sought recognition. He retired quietly in 1958, leaving behind a collection of notebooks filled with meticulous calculations and terse remarks. One entry, written in his final year at Vickers, reads, "The aircraft obeys mathematics, not opinions." It might have served as the epitaph for an entire generation of wartime engineers who built weapons not for glory, but for understanding. Today, A single Vickers S barrel and 2 reinforced Spitfire wing panels survive in museum storage, their labels faded, their origins rarely mentioned. Visitors pass them without knowing that they represent a moment when an elegant interceptor was transformed into a scientific instrument, a testbed that proved force could be mastered, and precision could be built. The 40mm Spitfire never saw combat, never made the headlines, and never carried victory markings on its fuselage. But its trials defined the boundary between art and calculation, showing that even a weapon born from rejection could measure the limits of an idea. In the quiet logic of post-war reports, its legacy endured not in emotion or triumph, but in numbers that still instruct those who build aircraft today. The record closes where it began, at Boscombe Down, February 1943. A Spitfire rises into the cold air, its long-barreled cannons glinting against the morning sky. Observers watch, pencils poised, noting each sound and vibration. No one speaks. They are measuring, recording, learning. In that silence lies the real victory, knowledge captured in flight. By 1960, Britain's air doctrine had entered the jet and missile era, yet the data collected from the Spitfire T project still circulated in engineering offices under the quiet classification historical reference, ballistic structures. The Royal Aircraft Establishment treated those wartime notebooks not as relics, but as foundations. Engineers designing the English Electric Canberra's gun installations referred to the same 1943 recoil deflection charts from Boscombe Down. In one marginal note, an RAE analyst wrote, "Initial 40mm impulse trials remain our only reliable record of sustained wing recoil tolerance." That endurance, mechanical, not symbolic, was the Spitfire T's true contribution. It had provided a set of numbers that no theory could have produced at the time. Those measurements defined how thin metal could flex under stress without failure, how hydraulic dampers could contain an instant of violent motion, how accuracy could be quantified across 1,000 variables. For the engineers who built Britain's next generation of strike aircraft, those equations were more valuable than any combat victory. In 1963, a classified Ministry of Supply report on the Hawker P.1127, later the Harrier, made direct reference to earlier single-seat heavy-gun firing data. Its authors cited the Vickers S experiments when testing the recoil vector of the new aircraft's Aden cannon. The lineage was intact. From the propeller-driven Spitfire T to the jet-powered Harrier, a straight line of engineering thought persisted: absorb recoil, maintain control, strike precisely. By then, Harold Percival was retired and living in Hampshire. Visitors recalled him as courteous, meticulous, and reluctant to discuss wartime projects. Yet among his papers, donated posthumously to the Imperial War Museum, one folder contained a copy of the original Farnborough test report. Across its cover he had written a single phrase in pencil: "It worked." At Boscombe Down, where the first prototype had flown 20 years earlier, the old grass strips had long been replaced by concrete runways. Jet engines screamed across the same sky once filled with the deep, deliberate roar of a Merlin 45. Technicians testing new armament sometimes found themselves reviewing the 1943 gunnery films, the black and white footage of a Spitfire in a shallow dive, 2 flashes beneath its wings, a column of dust rising from a wrecked tank. The imagery was grainy, indistinct, yet still used to illustrate the origins of airborne precision. In one of those reels, the camera shakes slightly as the gun fires. The aircraft steadies, smoke trails drift, and a voice on the range intercom calls out the impact reading. It is a scene without spectacle, no music, no celebration, only measurement. That calm pursuit of accuracy, born in a war fought amid chaos, had become the discipline of modern aeronautical science. By the 1970s, every Royal Air Force technical course on weapons integration included a lecture titled Historical Case Study, the Spitfire 40mm installation. The lecturer would display a single slide, Percival's schematic of the recoil cradle, and end with a simple observation: every modern cannon owes something to this. Students took notes without sentiment. They understood that innovation often begins not with success, but with persistence through failure. No replica of the Spitfire T was ever built. The surviving parts, a pair of modified wing sections, one cannon breech, and a rusted sight mount, remain stored at Duxford. Their metal is dull, the paint flaking, but the forms are unmistakable. Each is a trace of an idea tested under the pressure of necessity. The project that began as an act of improvisation ended as a blueprint for precision. Its data-shaped designs, its failures taught restraint, its existence bridged generations of engineers who believed that progress was not a triumph but a process. And though no pilot ever flew it in combat, the Spitfire T altered the language of air power. It proved that a fighter could be an instrument of calculation as much as courage. The records are still there in bound ledgers stamped Air Fighting Development Unit, 1943. The ink has faded, but the signatures remain legible. Each page tells the same quiet story: a test, a result, a lesson. In those lines, the legacy of the rejected cannon continues, not as memory, but as measurement, proof that even the smallest experiment, precisely recorded, can outlast the machines it once sought to perfect. By the late 1980s, Britain's aerospace industry had changed beyond recognition. Jet turbines had replaced piston engines, composite alloys had replaced riveted duralumin, and guided missiles had rendered gunnery almost an art of the past. Yet deep within the Ministry of Defence's technical archives, engineers still kept a thin, grey folder marked Spitfire VC, Special Armament Trials, Boscombe Down, 1943. It was consulted less for nostalgia than for precedent. The flight data within remained a baseline for understanding recoil vectors in lightweight wings, numbers that no simulation could easily reproduce. When British aerospace engineers designed the first production run of Harrier GR.7 aircraft, one of them, Alan Price, formerly of RAE Farnborough, found Percival's old recoil chart still referenced in the airframe load database. He later wrote in an internal memorandum, "We continue to build on empirical foundations laid by those who measured rather than theorized." It was an acknowledgement that the scientific continuity begun in wartime never truly ended. In aviation museums and lecture halls, the Spitfire's legend had become a symbol of beauty, agility, and victory. Few remembered that among its countless variants was one conceived not for speed or grace but for raw mechanical inquiry. The 40mm Spitfire T existed at the intersection of improvisation and discipline, an aircraft designed not to win battles but to answer questions. How much force could a fighter endure? How precise could a human be in a machine designed for survival rather than stability? Those questions would resurface again and again in British design philosophy. When the Panavia Tornado entered service in the 1980s, its low-level strike profile, fast, deliberate, precise, reflected the same logic that guided McKenna's 1943 dives at Lulworth Cove. The technology had advanced beyond recognition, but the principle remained unchanged: accuracy begins with understanding the limits of structure, motion, and recoil. Percival did not live to see those aircraft fly. He died in 1974, his contributions unpublicized outside technical circles. At his funeral, a colleague from Vickers read a line from one of his notebooks: "The measure of success is not approval, but repeatable data." It could have served as the quiet creed of British engineering through the post-war decades, dispassionate, meticulous, and deeply human in its insistence on precision. At the Imperial War Museum, a curator catalogued the remaining pieces of the experiment in 1991, 2 modified wings, 1 Vickers S barrel, and a single 16mm film reel labeled Trial S12. The reel shows less than 3 minutes of footage: a Spitfire banking over chalk cliffs, 2 flashes beneath its wings, a distant column of dust rising over a wreck. No commentary accompanies it, only the whir of the projector. Visitors seldom recognize the significance, yet for the few who study the engineering notes, that grainy image captures a pivotal transition in modern warfare, the moment when intuition gave way to measurement. Every modern aircraft that carries a cannon, be it a Typhoon, a Harrier, or a Lightning, operates under principles first confirmed by that brief experiment over southern England. Each burst of fire, each vibration absorbed, each recorded impulse can trace its ancestry to Percival's rejected gun and the Spitfire that carried it. The names have faded, but the method remains: test, observe, refine. Outside, the airfield at Boscombe Down endures as a testing site. The runways stretch across the same Wiltshire grass where mechanics once pushed a prototype into position before dawn. On quiet mornings, when the wind carries the distant echo of jet turbines, it is possible to imagine the sound of a Merlin engine rising once more, steady and deliberate, followed by two brief detonations, the measured rhythm of knowledge in flight. That is where the record ends. No triumph, no lament, only data preserved, lessons inherited, and a single enduring truth: progress is built not from what succeeds, but from what survives to be studied. By the turn of the 21st century, the story of the Spitfire T had all but disappeared from public view. The aircraft existed in no commemorative exhibit, and its name appeared in no restoration registry. Yet inside the engineering departments of BAE Systems and the Defense Science and Technology Laboratory, the trial reports from 1943 still circulated in digitized form. The numbers were timeless. Structural stress, recoil dampening, and firing dispersion did not age the way technology did; they remained constant variables in the study of airframe tolerance. In 2002, when technicians at Wharton calibrated vibration sensors for the Eurofighter Typhoon's 27mm Mauser cannon, one of the reference documents cited was AFDU Spitfire VS-12, the same Boscombe Down test file that had once been typed on thin wartime paper. A notation in the margin read simply, "Historical load data verified against modern finite element model." 60 years after its creation, Percival's empirical measurement still aligned with digital simulation within 2 decimal points. At the Royal Aeronautical Society Centenary Symposium in London, a retired armament engineer presented a slide of that 1943 Spitfire. He spoke without rhetoric. This was not a weapon, he said, it was a question answered in metal. The audience, composed mostly of young aerospace designers, regarded the image in silence. For them, it represented the beginning of modern testing culture, the insistence that every idea be proven in the physical world before theory could claim authority. Meanwhile, in the archives at Duxford, a conservator completed the restoration of the surviving Vickers S barrel. The steel was cleaned, sealed, and mounted beside a small plaque. It bore no patriotic inscription, only factual detail: 40mm Vickers S cannon. Fitted to Spitfire V.T. Trials, Boscombe Down, 1943. Visitors who passed through the display rarely noticed it, but for engineers and historians the object symbolized a turning point, the moment when wartime improvisation evolved into post-war method. Every successive generation of aircraft, Hunter, Harrier, Tornado, Typhoon, carried something intangible from that experiment: the balance between force and control. The Spitfire T's designers had not sought elegance or fame, they had sought to understand the limit of structure under stress. In doing so, they gave British aviation its scientific spine. Late in his life, squadron leader McKenna was interviewed for an oral history program. When asked what he remembered most from the tests, he paused before replying, the silence after the shot. It was the instant, he said, when every vibration and calculation became proof. That moment, frozen between motion and understanding, defined what it meant to turn flight into science. Today, the old airfield at Boscombe Down still functions as a proving ground for new technologies. The sound of jet engines has replaced the hum of Merlins, but the ritual is the same. Engineers observe, record, adjust, and learn. Somewhere beneath the layers of asphalt lies the patch of grass where the Spitfire VT once fired its first round. The crater has long been filled, yet the data it produced continue to guide aircraft that now break the sound barrier. The experiment that began as an act of necessity became a foundation for precision warfare and aerospace engineering. It needed no monument, no memorial flight. Its legacy is measured not in victories, but in equations: every recoil absorbed, every rivet tested, every angle recorded. In the long continuum of air power, the Spitfire T stands as proof that knowledge, once captured, never truly disappears. It travels quietly through generations of engineers, encoded in design tolerances and flight manuals, shaping machines whose creators may never know its name. And so the story ends where technology begins, not with glory or loss, but with endurance of understanding. The rejected cannon did not win a war, it built a discipline. In the measured cadence of history, that is its lasting victory. By 2020, the last surviving technicians who had witnessed the Boscombe Down trials were gone, but their reports endured in digitized repositories and academic citations. Inside the Imperial War Museum's document vault, the file once labeled AFDU Spitfire VS-12 had been scanned in full, 57 pages of measurements, typed tables, and marginal notes. Each page bore the neat pencil marks of engineers long deceased. Even now, the handwriting remained precise, unhurried, as if written with the expectation that someone, decades later, would still find value in the numbers. That expectation proved correct. Modern aerospace researchers still use those data when modeling gun recoil dynamics for light airframes. In 2021, a Cambridge engineering thesis on energy dissipation in wing root structures cited the Spitfire 40mm installation as the earliest documented instance of successful recoil absorption in a single-engine aircraft. The citation, dry and academic, linked a wartime improvisation to the mathematics of the present. The continuity was almost invisible, yet total. The principles born in the tension of war, balance, distribution, precision, had become the quiet constants of modern aviation. Each new generation of aircraft, whether stealth or supersonic, obeyed them. When a Typhoon's cannon fired without shaking its fuselage, or when a drone absorbed recoil from an onboard payload, the same lineage could be traced back through 7 decades of progress to a hangar in Wiltshire where a single Spitfire fired into a derelict tank. Occasionally, curators revisited the story. In 2019, a small exhibition titled Engineering the Impossible at Duxford included the Vickers S barrel beside Percival's engineering notebook. The display offered no dramatization, only a concise text, from rejection to reference. This gun proved that stability could be engineered. Visitors lingered briefly, then moved on to the better-known aircraft beyond the glass, the graceful MKIXs, the late-war Griffon models, the fighters that carried victory in their names. Few paused to consider the quiet logic that connected them all. But in the background hum of that museum, the air still seemed to carry an echo, the faint mechanical rhythm of a Merlin idling at Boscombe Down in 1943, the sound of pencils scratching figures onto a clipboard, the flat crack of 240mm rounds striking armor. That noise, captured once on film, represented the moment when the language of flight shifted permanently from instinct to data. The Spitfire T remains almost absent from the popular memory of the war. It fought no battles, earned no decorations, and destroyed no enemy. Yet in the files of the Royal Aircraft Establishment and the lecture notes of aeronautical engineers, it persists as a point of origin, the first proof that precision could be engineered as deliberately as speed or power. Every generation since has built upon that proof. From jet-age strike aircraft to precision-guided munitions, the idea that accuracy is a measurable, designable property began with that experiment. It demonstrated that knowledge is cumulative, that even a failed prototype can define the boundaries of the possible. Now, when historians trace the evolution of air-to-ground warfare, they often begin not with the Typhoon or the Mosquito, but with the quiet entry marked Spitfire Mk V, T, Vickers S cannon trial. It stands as the unspoken bridge between improvisation and innovation, between a desperate wartime modification and the science of precision that followed. And somewhere, preserved in the stillness of a vault or the silence of a data archive, the numbers remain: velocities, recoil loads, wing deflections. Each figure is a fragment of the moment when Britain's most elegant fighter became, for a brief season, an instrument of measurement. In those measurements lies the Spitfire T's enduring legacy, proof that progress does not always roar across the sky. Sometimes it whispers through paper, ink, and the calm certainty of tested truth.